Good morning. We are still in our series of outlining the basic design of different types of cable-stayed bridges. We have dealt with steel bridges and with concrete bridges. Now today we will talk about composite cable-stayed bridges, combining both materials in the most economic way. Composite cable-stayed bridges, very generally, have a concrete roadway slab resting on some sort of steel girder grid. We do this for two reasons, basically. First of all, the roadway slab as an orthotropic deck is on one hand rather expensive in steel, and also outside Germany the fabricators do not have this sophisticated equipment to weld an orthotropic deck, which is quite involved, and it needs turntables and automatic welding equipment and so on. So the roadway from concrete is more economic, especially abroad. And secondly, we know that a very important force in the roadway slab is a compression. The inclined cable exerts compression onto the beam. And we know to carry compression is more economic in concrete than in steel. Concrete loves compression. Steel less so. Always comes the problem of buckling. So, on the other hand, in bending, where we have tensile forces, steel is advantageous. Concrete itself cannot carry reliably tension. We have to reinforce it with steel or something like that. So we then combine the compression, the way to carry compression very well for the concrete, and the possibility to carry bending, meaning tension at the underside, in steel. That's why we combine the two with concrete on top, acting as roadway slab and compression member and top flange of the overall cross-section in compression, and steel underneath for bending and also carrying compression. The overriding design consideration for a composite cross-section is to keep away tensile forces from the concrete as much as possible. Now, in transverse direction, we therefore only use two outer cable planes which create in transverse direction a beam simply supported at the outside. That means we have only a positive bending moment, and therefore the concrete acts as top flange of a simple supported girder, meaning it's in compression, not only from permanent load but also from life load. If we put life load on top here, from the transverse bending we get compression. In longitudinal direction, as I already mentioned, we have the compression from the inclination of the stay cables acting in compression. So there is a lot only in the center of the bridge, where the cables, so to say, end from both sides and the compression force goes to the two towers. There is little compression, and there we may want additional reinforcement, or there is a little trick. If we fabricate the beam too high with a upwards camber and then let it down, then we get from this frozen in moment, again, compression in the top flange as bending from bending. Part of it creeps away, but part remains. So that's a little trick. In this way, just by natural means, we get compression into the roadway slab transversely and longitudinally, and do not need to post-tension the roadway slab, which is wrong and uneconomical. Because if we post-tension the roadway slab, concrete tends to creep away from the compression, which means a considerable part of any post-tensioning in the roadway slab would run away from the roadway into the steel, which does not creep. And that just there is where we do not want the compression. So we do not post-tension a concrete roadway slab because the post-tensioning would run away into the steel. We just use it from natural means. Also, it's clear that it is unreasonable to use a central cable plane for an orthotropic deck, as we had with steel, for example, or all concrete. Sometimes it may be advantageous, but in this case then we have the negative bending moments here as two cantilevers, which gives us high tension in the roadway slab. That's basically wrong. We never use one central cable plane with orthotropic, but only two outer cable planes. We look into the overall beam, and we see it here. A very efficient cross-section is a steel girder grid with main girders at the outside and cross girders across in between. We connect the stay cables directly to the main or longitudinal girders. That's where the force has to go, the shear has to go into the webs here. Don't try and anchor it here and then we have to transfer it again. Direct transfer of forces. And then we cover the steel girder grid by a concrete roadway slab that can either be cast in place or precast. Now, precast slabs, as I've outlined here, which will be placed here, have the advantage that when they are being installed, they have an age maybe of 1 year. They are cast on site before. That means they have strongly reduced shrinkage and creep characteristics, which of course is advantageous, and it can mean fast or rapid forward going on site, rapid progress on site. Their shortcoming is that, of course, we do have joints. We place the slabs here, then we have longitudinal joints, we have transverse joints, and in addition, we have to place shear studs on top of the cross girders to get the rigid connection between the steel grid and the concrete slab. So these shear studs protrude into pockets, which we have here, and all this has to be closed by cast-in-place concrete with overlapping reinforcement in the joints. Such joints are always, in general, weak spots in a roadway slab. We'd rather try to avoid them. However, here we can do it because the joints are longitudinally and transversely permanently under compression, contrary to other structures. So it can be very advantageous to use precast slabs. The other possibility, of course, is to use cast-in-place deck. We will see examples for that as well. There we have the disadvantage that we have to install forms, shuttering between the cross girders, cast in place, and it takes longer and it has more shrinkage and creep. So it's a trade-off. Both methods, precast or cast in place, are possible. They have their pros and cons. Normally the contractor decides what for him, with his equipment and his experience, is the most economical. Just to make it complete, there are additional composite features in addition to the roadway slab in concrete and steel girder grid. There are examples where we have a concrete, say, beam with steel cross girders in between here. So this was used for weight purposes. We needed to bring the weight down for the East Huntington Bridge. We'll show that example later. So that's a partial composite solution. And in addition, we can use a composite solution for stiffening orthotropic decks. It's called today, there's a development in Germany also, and we call it orthocomposite. Now, there are two advantages. First of all, asphaltic concrete sometimes doesn't stick so well to the steel. There's delamination. You have to repair it all the time sometimes. Now here, if we put a concrete layer on, we can use some shear studs and get a real good connection. Furthermore, on an orthotropic deck, when the temperature drops, slippery ice forms earlier, faster than on a concrete deck, which takes longer time to cool down when the temperature goes down. So, and in addition, we can use the concrete to stiffen the orthotropic deck itself, which means we may be able to increase the distance, which is normally 300 millimeters, to say 400 millimeters, as was done here for the Sarate-Brasilago bridges. And instead of using a 12 or 14 millimeter thick top steel plate, we may reduce that maybe to 10 millimeters. So in special cases, in some countries, it may be more economic. Just for good measure, I wanted to mention it. Now, when we have these three types of cable-stayed bridge beams, steel, concrete, composite, when do we use what? Meaning, where is the economical range for these different types? And I know many years ago, I made this curve with an engineer of mine, and we tried to fiddle around with unit prices, and it can only give an indication, but very generally, we can remember the lower spans up to something like 400 meters are very often economical in concrete. Say medium spans, 400 to 600, 700 meters, may be often economical as a composite beam. And the long spans, say above 700 meters, are still the domain of steel. One cannot really say that's always the case. It depends on country. Norway, they build concrete with 530 meter long spans because it's a concrete country. In the US, steel composite will start much earlier. But roughly speaking, up to 400 meters concrete, 400 to 700 meters composite, and above that, steel, very general. And that's what you, if you want to, can read out of this very simple curve. Now, having discussed the basics and the basic idea of composite, we now show examples. Just as we mentioned spans, where do we stay? It started, we'll see it with a very small bridge. That's just for curiosity, and because the bridge was in Germany. But then, in earnest, we started in 1970 with something like 450 meters, you see that? And the world record still is 602 yang pu. So what I told you, above 400 to 700 shows in the record spans. The very first one, normally overlooked, small bridge in near Karlsruhe, Büchenau, across the railway, completed already in 1956. Very ingenious. They had the beam built too high against the final state, installed the cable slack, and lowered the beam down on a predetermined level, and by that lowering down they stressed the cables. And it worked. Homburg was checking engineer and was the idea behind there, but that was again more or less forgotten. It was a unique bridge. People didn't take it up until in the early 70s in India, in Calcutta, a second bridge had to be built across the Hooghly, which is a tributary of the Ganges River. There is one Hooghly river bridge, steel truss from Freeman Fox, built before 1900, and that's overloaded. The next bridge was required, and there was a long ago engineers change until finally my company, that was in the late 60s, before my time, got the job. And finally what came out was a world record during the design stage, 457 meter main span bridge, 1,500 feet. Of course, at that time it was all in feet and inches. So the span was 1,500 feet. We can remember that very well. And if we translate that, it's 457 meters. And the design condition was use only local material in India and use it labor intensive, because we want to employ our Indian workers as much as possible. So, use Indian steel. That means at that time Rourkela was the steelworks in India, and the steel they produced was not weldable. So, no orthotropic deck. At that time, unusual. So, no orthotropic deck. What could you do? You use a concrete deck. And then they also didn't have high-strength bolts themselves. So, all connections had to be riveted. Rivet sind Nieten. You know, you heat them up and then you bang them. You never heard of it and you've never used it. That's something from the 19th century. But it's the only cable-stayed bridge which has been riveted. And rivets are not so nice for concentrated force introduction. You know, when you have on a small space high forces, and that's at every cable anchorage point, we introduce a concentrated force into the beam. So one had to think all sorts. Anyway, finally, a very ingenious system. Today we say that's regular, but that was all new. A steel girder grid with open cross-section, main girder directly connected, cross girders cast in place, roadway slab. Quite a step. I told you why, otherwise it would have been a steel deck and everything, but it had to be done, so engineers were thinking about. But the bridge never had the world record, although it made the big jump, because as it sometimes happened in India, it took 20 years to build the bridge. 1974, that's why I'm so cheeky and say here 1974. Well, the design was completed. The bridge was opened in 1994. At that time, of course, the world record was long gone. But it was an ingenious design. And Professor Jörg Schleich, you may have heard from him, was in charge. At that time, he was still a partner in my company, Leonhard Andre and Partner, when I started there in the early 70s. I was for some time nominated as resident engineer in India, but then I had to go to the US, and my wife wasn't so unhappy about it. We had a newborn child, and she wasn't too keen to go to Calcutta with a newborn child. Anyway, and his able assistant, Rolf Bergermann, supervising engineer at that time, they were the two who designed the bridge. I think in 1981, the Sunshine Skyway Bridge in Tampa, Florida, was hit by a ship, fell into the water, 35 people dead. So it was required very quickly to build a new bridge. We will see that in ship collision. I show a picture. And we designed this as a fairly new design along some lines of Hugli and some new ones. But we lost it in the US in competition against Jean Muller with another concrete cable-stayed bridge, because, I keep saying, some bad foundation design in the approaches which we didn't do. And it was a very nice design, and it still hurts that I spent 2 years in the US that we were not successful. The next bridge which took up these design ideas which we had developed for the Sunshine Skyway Bridge. Just briefly a remark. In Germany, at that time, the codes required a limitation of tensile stresses in the concrete roadway slab, in service load. And that would have meant you would have to post-tension in Germany the concrete roadway slab, which is uneconomic, as I told you before. And that's why there were no composite cable-stayed bridges in Germany until recently. But in the US, we said, what the hell? The American codes didn't know about, these finer points we were considering here. And so we said, okay, we use a lot of finely spaced reinforcement for crack control and have safety in the ultimate state. And so we could design this bridge, which would not have been possible at that time in Germany. Now it is. The German codes are changed. There are no stress limitations under service load anymore, so we can do that. Anyway, these considerations were taken up for a bridge in Canada, Annacis Bridge across the Fraser River near Vancouver, British Columbia, with a main span of 465, was same design as our Sunshine Skyway, basically. They had just one additional idea, which isn't bad. Instead of connecting the cables to the side of the webs, they built a web extension and anchored then directly, even more directly to the web, the stay cables. The problem, of course, is this joint. Of course, you must not weld this extension on top of the top flange, because then you tear, you have through thickness tensile, and you get what we call in English lamellar tearing. You may get horizontal cracks, Lamellenbrüche heißt das in Deutsch. So you must not pull transversely on a plate, but you can cut a pocket into the plate and then have a butt weld here, which has the same strength as the structure itself, and the plate then protrudes through here. That was a neat idea. Two engineers, friends of mine, Peter Buckland and Peter Taylor, both from British origin, went to Canada and did all the major bridges in Canada. They have been doing. We've worked with them on several. Now, in between, we had to design a bridge across the Mississippi at Burlington. Nothing spectacular, just you may remember, since I worked for 15 years in the US, between 70 and 85, there was always a competition. There was a concrete design and a steel design given to different designers, and the alternate, which was bid low, was built. So we didn't get Sunshine Sky. Well, here, both alternates were given to our designers, so that was very nice. Whoever won, it was our design. In this case, it was composite, but they normally didn't do that. Now, the next record, and still in existence, is the Yangpu Bridge in Shanghai in 1993 with 602 meters. In general, a conventional design. I was involved because China wanted to borrow about 100 million US or something from the World Bank, and the World Bank said, yeah, we'll check it before we give you the money. And so there was an international checking panel with the top American, top Japanese, and myself as engineers, and we checked all that, and it was all okay. As well the design, as well as the construction, we looked. They did it in 2 places. It was all very nice, and I had to give a TV interview after signing this loan, and the TV was there, and I was asked, I said, what do you say about the design? Well, I say it's all very nice done, but I say that with, as we have a German saying, a laughing and a crying eye. Laughing because as a checker you are happy if everything is fine and you don't have to tell them you have to do it all again. Now, the crying was, I realized immediately that the Chinese are good enough to design all their bridges themselves. So for me, as member of Leonhard Andre and Partners, a German consultant who likes to do work overseas, no work in China, and that was the case. The Chinese can do it very well themselves. Heinola Bridge, we will see again 2 things. It has a nice harp arrangement, looks nice, and all the bridge, the full length, was done by incremental launching with auxiliary piers here, and then the cables were installed, the auxiliary piers removed. We'll see that again. My friend Esko Yavenpay was the engineer for that. An interesting bridge in Hong Kong is the Kap Shui Mun Bridge. Hong Kong had infamous airport, Chep La Kok, which was right in the middle of high-rise buildings. And when you came into that thing, people were a little bit afraid that the plane would hit a high-rise tower. It was very crowded. So, and of course there's not much space in Hong Kong. Kowloon is very crowded. They said, okay, we'll use the island of Lantau, flatten it partly to get the airport, and then we have from Kowloon go over to Lantau, which is an island in the Bay of Hong Kong. And there's a major suspension bridge, Tsinghua, done by friends by Mott MacDonald, and we had this, the other part, the Kap Shui Mun. This is Kap Shui Mun over this Rambler Channel, and interesting is that it's a double-deck bridge with 6 lanes of traffic on top, and regularly 2 rapid transit railway lines at the bottom plus. If we have one of these typhoons, which are current, which appear often in Hong Kong, you cannot use this, cars would be blown away. So we need emergency lanes in case of a typhoon, and they are also here for ambulances, police, and things like that, in addition to the railways here. And now, this was designed, quite unique, as a composite structure. We have steel frames, we have steel webs, and we have concrete top and bottom slabs. And since we have the railway here, then we always have a depth of something like 8 meters, and close cable spacing, so it was possible to lift complete sections, all the steel, all the concrete in, just straight up with strand lifting equipment. Those weigh in excess of 500 tons. That's a lot to lift, but possible because we have this great depth. 8 meters is possible. An interesting bridge I did was again in the US, in Texas, across the Houston Ship Channel, which goes directly into the Gulf of Mexico and all. That's the oil center of the US. All the oil tankers go in and out. There was a tunnel until then, but the tunnel was too small and was old, so a new connection had to be built, a bridge. First of all, because of the heavy ship traffic, I think it's 55 meters, 180 feet, something like that. It's all, of course, still today feet and inches in the US if we calculated PSI instead of Newton per square millimeters, and you get used to it. So, but I make it all metric here. So 50 meters high, then we needed something like 380 meters also from ship collision. And because everything in Texas is bigger and better, we needed 8 lanes, 4 lanes in each direction with full shoulders on each side. So we had actually 6 lanes going to, 6 lanes coming back. Would mean a very wide bridge. And we started out with 2 cable planes, I think it was about 50 meters or so wide, 2 cable planes at the outside, and found out that we needed as much steel. We had the composite alternate. Jean Muller had the concrete alternate. So we had steel main girders. The weight of that was equal to the weight of the cross girders, which is highly unusual. And we were in competition with Jean Muller, against whom we lost Sunshine Skyway, and this time I said we win. So we were then said, okay, we use 2 separate beams with a total of 4 cable planes, and in that, then the steel required transversely for the cross girders was only 1/2 of the longitudinal. So we saved 25% of the steel to start with. Of course, basically we had the same amount of cable steel, everything else. So that's why we made a twin cable stayed bridge. Then came the towers. We wanted A's on top, and finally we came, after some consideration, to the solution that we connect the 2 aims and we have a truss frame, 2 separate foundations, and now wind transversely on the cables and on the beam acts on a truss, not in bending, in this constellation, which means we basically carry the horizontal wind forces in tension and compression in the tower legs, not in bending. And because we wanted to win the thing, now we really went to the minimum 2.1 meter, 7 feet actually, but 2.1 meter across here for 150 meter high. It's very slender. So 1 foot wall thickness, 30.5 centimeters constant. 4 layers of reinforcement. It's getting a little crowded. And then here it's all overlapping. But it worked. I'll give you a special lecture next semester on the construction of this bridge. It's quite unique. And the end of the story, we won. So that's what we wanted. And that's the name of the game. I mean, in bridge design, you want to win. It's always competitive design. It's one against the other. And the final prize counts everywhere in the world. Okay, another interesting bridge, Öresund Bridge from Denmark to Sweden. Also, the whole crossing with a great belt and so on has a railway, so we didn't do it in detail, was involved. There was chosen a truss with the railway underneath, roadway on top, and of course if you have the railway underneath, it's always better to use a truss than to use a box, because people running in the trains over the bridge, they can look out through a truss. It's a clear picture of the sea, and it looks very nice, instead of having closed webs in a box where you're in a tunnel. So from that reason alone, although a truss is not necessarily less expensive than a box, it's always nice to have the railway running in a truss to give people the view. Some others, I was checking engineer Uddevalla in Sweden. Similar, you know that already by now. This, what we did in Sunshine Skyway, has been taken over by many with an open cross-section. We had some ship collision problem, we'll find it there again. Kolbäcksbron, also I was checking engineer in Sweden. My friend Eljan Jure designed it from Norway. Again, the whole bridge was incrementally launched on auxiliary piers. We do it now also in Germany, as I told you, since people have seen the light with the tensile stress limitation under service is gone. We make crack control and dimension, size it in ultimate state. This is only in 2006 the second composite cable-stayed bridge in Germany, after the tiny little one in Büchenau, because it took so long to change the code. It goes over the railway bridge, otherwise it's typical as we did it. And the next one, very close to here, Niederwarta Bridge, also a nice composite cable-stayed bridge, which is possible now. I think it's not, the bridge is done. It's not in service because I think the approach roads are not done or something like that. But you can see it, it's what, 10 kilometers from here? Other interesting composite cable-stayed bridge across, the third bridge across the Orinoco, is also Hugo Chavez, whom you may know as a politician there, decided to spend some of the oil money on improving the infrastructure, which means in Venezuela crossing the Orinoco with a fixed crossing. Normally there are only ferries, and there's 10 to 12 meter up and down going the water level over the run of the year. It makes it all tricky. And so we've done, there was an old truss, the first, and we've done the second, the third, and are doing the fourth now, crossing in order to open up the country with infrastructure. And very clever, they say the government, although we don't have a railway yet coming to the bridge, we designed the bridge to have a railway. So later on, once we build the railway, then the bridge is ready. So this is why all these Orinoco bridges we're doing have, in this case, only one railway track, although there will be no railways left and right today, but later on. And again, it's very long bridges, 10 to 12 meter difference in water level, which means very long bridges so that the railway doesn't get wet feet at high water level, 10, 12 kilometer long approaches. Long spans, very bad soils conditions, so the cross-section then from the approaches is governing the bridge, and that was pulled over through the cable stay. It works well. So, this should give you an overview over composite cable stay bridges. They advantageously combine the advantages of concrete and steel. Concrete on top for local wheel load distribution, plus carrying a large part of the compression force, and steel underneath for ease of construction. We will see that later in special lectures, and also for taking the mostly positive bending moments from live load, which gives tension at the bottom, where steel is very good in tension. Concrete is good in compression. And that's why this combination is basically, for suitable situations, a very economic solution. And as I pointed out again today, in real life, what I'm talking about, competition is the name of the game. It's always a competition, and we want to win. So we have to find the most economic design, which is as good and stands up as long as other designs, which apparently are more expensive. Okay, thank you.